So I took some screen captures from the Khan Academy exercise on correlation coefficient intuition, and they've given us some correlation coefficients, and we need to match them to the various scatter plots. On that exercise, there's a little interface where we can drag these around in a table to match them to the different scatter plots. And the point isn't to figure out how exactly to calculate these. We'll do that in the future, but really to get an intuition of what we're trying to measure. And the main idea is that correlation coefficients are trying to measure how well a linear model can describe the relationship between two variables. So for example, let me do some coordinate axes here. So let's say that's one variable. Let's say that's my y variable. And let's say that is my x variable. And so let's say when x is low, y is low. When x is a little higher, y is a little higher. When x is a little bit higher, y is higher. When x is really high, y is even higher. This one, a linear model would describe it very, very, very well. It's quite easy to draw a line that essentially goes through those points. So something like this would have an r of 1. R is equal to 1. A linear model perfectly describes it, and it's a positive correlation. When one increases, when one variable gets larger, then the other variable is larger. When one variable is smaller, then the other variable is smaller, and vice versa. Now, what would an R of -1 look like? Well, that would once again be a situation where a linear model works really well, but when one variable moves up, the other one moves down, and vice versa. So let me draw my coordinates, my coordinate axes again. So I'm going to try to draw a data set where the r would be -1. So maybe when y is high, x is very low. When y becomes lower, x becomes higher. When y becomes a good bit lower, x becomes a good bit higher. So once again, when y decreases, x increases, or as x increases, y decreases. So they're moving in opposite directions. But you can fit a line very easily to this. So the line would look something like this. So this would have an r of -1. And an r of 0, r is equal to 0, would be a data set where a line doesn't really fit very well at all. So I'll do that one really small since I don't have much space here. So an r of 0 might look something like this. Oh, maybe I have a data point here, 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 maybe I have one there, there. And it wouldn't necessarily be this well organized, but this gives you a sense of things. How would you actually try to fit a line here? You could equally justify a line that looks like that, or a line that looks like that, or a line that looks like that. So there really isn't, a linear model really does not describe the relationship between the two variables that well right over here. So with that as a primer, let's see if we can tackle these scatter plots. And the way I'm going to do it is I'm just going to try to eyeball what a linear model might look like. And there's different methods of trying to fit a linear model to a data set, an imperfect data set. I drew very perfect ones, at least for the r equals -1 and r equals 1. But these are what the real world actually looks like. Very few times will things perfectly sit on a line. So for scatter plot A, if I were to try to fit a line, it would look something like that. If I were to try to minimize distances from these points to the line, I do see a general trend that when y is, if we look at these data points over here, when y is high, x is low, and when x is larger, y is smaller. So it looks like r is going to be less than 0 and a reasonable bit less than 0. It's going to approach this thing here. And if we look at our choices, so it wouldn't be r equals 0.65. These are positive, so I wouldn't use that one or that one. And this one is almost no correlation. R equals -0.02. This is pretty close to 0. So I feel good with r is equal to -0.72. R is equal to -0.72. Now I want to be clear. If I didn't have these choices here, I wouldn't just be able to say, just looking at these data points without being able to do a calculation, that R is equal to -0.72. I'm just basing it on the intuition that it is a negative correlation. It seems pretty strong. The pattern kind of jumps out at you that when y is large, x is small. When x is large, y is small. And so I like something that's approaching R equals -1. So I've used this one up already. Now scatterplot B, if I were to just try to eyeball it, once again, this is going to be imperfect, but the trend, if I were to try to fit a line, it looks something like that. So it looks like a line fits in reasonably well. There's some points that would still be hard to fit, and they're still pretty far from the line. And it looks like it's a positive correlation. And when x is small, when y is small, x is relatively small, and vice versa. And when as x grows, y grows, and when y grows, x grows. So this one's going to be positive. And it looks like it would be reasonably positive, and I have two choices here. So I don't know which of these it's going to be. So it's either going to be r is equal to 0.65 or r is equal to 0.84. Now let's look at scatter plot C. Now this one's all over the place. It kind of looks like what we did over here. What does a line look like? You could almost imagine anything. Does it look like that? Does it look like that? Does a line look like that? These things really don't seem to, there's not a direction that you could say, well, as x increases, maybe y increases or decreases. There's no rhyme or reason here. So this looks very non-correlated. And so this one is pretty close to 0. So I feel pretty good that this is the r is equal to negative 0.02. In fact, if we tried, probably the best line that could be fit would be one with a slight negative slope. So it might look something like this. It might look something like this. And notice even when we try to fit a line, there's all sorts of points that are way off the line. So the linear model did not fit it that well. So r is equal to negative 0.02. So we use that one. And so now we have scatterplot D. So that's going to use one of the other positive correlations. And it does look like, there is a positive correlation when y is low, x is low, and when x is high, y is high, and vice versa. And so we could try to fit something that looks something like that. But it's still not as good as that one. You could see the points that we're trying to fit. There's several points that are still pretty far away from our model. So the model is not fitting it that well. So I would say scatterplot B is a better fit. A linear model works better for scatterplot B than it works for scatterplot D. So I would give the higher R to scatterplot B and the lower R equals 0.65 to scatterplot D. R is equal to 0.65. And once again, that's because with a linear model, it looks like there's a trend, but there's several data points that really, more data points are way off the line in scatterplot D than in the case of scatterplot B. There's a few that are still way off the line, but these are even more off of the line in D.